Have you ever heard of particles that seem to follow rules we do not have yet? In textbooks, the universe looks tidy, neat equations, clean diagrams, everything behaving the way the math says it should. But in real experiments, tiny specks of matter keep misbehaving. They appear where they should not, vanish too quickly, lean away from the predictions we trusted for decades. Each result is like a quiet reminder that our best theories are only approximations. Tonight, we are going to slow down and walk through this edge of modern physics, where impossible numbers keep showing up on the screen. If calm, careful puzzles like this are your thing, a gentle like and subscribe helps others discover it too. Settle in and let us see how broken our physics really is. Look around the room. The objects near you may seem very different from each other, but at a basic level, they are built from the same simple ingredients. The skin on your hands, the chair you are sitting on, the metal inside a phone or computer screen, and the air in front of you are all made from atoms. Each atom is built from three main kinds of particles: protons and neutrons in the center, and electrons moving around that center change how many of each you have or how they are arranged, and you get a new substance. Wood, plastic, metal, water, living tissue, all of them are just different patterns of these same basic pieces. This idea does not only apply to what is close by. If you think about Mars, the red planet in our own solar system, the story is the same. Its rocks and dust are made from atoms with protons, neutrons, and electrons. If you go much farther in your mind, out to the Andromeda Galaxy with its hundreds of billions of stars, the pattern still holds. Look across a big part of the observable universe, as far as our best telescopes can see, and everything that counts as normal matter appears to follow the same recipe. Wherever we point our instruments, the matter that shines, glows, or sits in cold clouds seems to be made from these familiar particles. At first, that might feel almost boring. Of course, the universe is made of atoms. That is the picture we all learn. But hidden inside that simple picture is a puzzle. Physics does not just allow for this kind of matter. It also allows for another kind, called antimatter. In fact, our best theory of particles suggests that for every type of matter particle, there should be a partner with the same mass but the opposite electric charge. So if we have electrons with a negative charge, there should be anti-electrons with a positive charge. If we have protons with a positive charge, there should be antiprotons with a negative charge. The equations that work so well for regular matter say that antimatter should be just as real and just as common. If that is true, we might expect to look out into space and see a universe filled with both matter and antimatter in large amounts. We might imagine galaxies made of matter in one region and galaxies made of antimatter in another, or mixtures of the two. But when astronomers observe the sky, what they find looks very one-sided. The stars, gas clouds, and galaxies we study appear to be made almost entirely of ordinary matter. We do not see large regions of antimatter shining back at us. The mystery here is not that our telescopes show something strange that we cannot explain. It is that they do not show something our theories almost demand: a universe just as full of antimatter as of matter. Before digging into that big puzzle, it helps to be clear about one thing. Antimatter is not just a made-up idea from science fiction. It is a real part of nature. It is built into a framework physicists use called the Standard Model of Particle Physics, This model is a collection of particles and rules that describe how they behave and interact. It has been tested in many experiments, and it works very well in most situations we can reach. Inside that model, antimatter is not an add-on. It is built in from the start, and we have been able to produce and detect antimatter particles in laboratories for almost 100 years. The first solid evidence for antimatter did not come from a movie or a theory on paper, but from a device called a cloud chamber in the early 1930s. In 1932, a physicist named Carl D. Anderson at the California Institute of Technology set up an experiment to study high-energy particles coming from space. These incoming particles are broadly called cosmic rays. They are mostly protons and other atomic nuclei that travel through space at very high speeds and sometimes hit Earth's atmosphere. A cloud chamber is a simple but clever tool. You take a sealed container filled with a gas that is cooled and nearly ready to condense into droplets, like air just about to form a fog. When a charged particle flies through this gas, it can knock electrons off the atoms in its path and leave behind a trail of ions. These ions act as tiny seeds that allow the gas to condense into visible droplets along the particle's path. The result is a thin, cloudy line that shows where the particle went. If you place the whole chamber inside a magnetic field, the path of each charged particle will curve. The direction and amount of curvature depend on the particle's charge and mass. A lighter particle bends more strongly. A heavier one bends less. A positively charged particle curves one way. A negatively charged particle curves the opposite way. Anderson used such a chamber, immersed in a magnetic field, to watch the tracks left by cosmic rays as they passed through. His first goal was to sort out what kinds of particles were pouring down on Earth from space. By measuring how the tracks curved, he could estimate both the charge and the mass of each particle that left a trail. But when he examined the photographs from his apparatus, he noticed something that did not fit the known list of particles at the time. Among the tracks, there were clear signs of negatively charged particles whose behavior matched what was already known about electrons. Their curvature and energy lined up with the known mass of the electron. That part was expected. But Anderson also saw tracks from positively charged particles that bent almost exactly the same way as the electron tracks. They were not heavy enough to be protons, which were the only well-known positively charged particles at that time. The amount of bending suggested that these particles had a mass very close to that of an electron, but with the opposite charge. This was not just a small detail. A particle with the same mass as an electron but a positive charge had never been seen before. The tracks in the cloud chamber were clear and repeatable, so they could not be ignored. These new particles were eventually named anti-electrons, and later given a shorter name, positrons. The posit in positron hints at their positive electric charge. For showing that these particles actually existed in nature, Anderson was awarded the Nobel Prize in Physics in 1936. While Anderson was taking photographs of particle tracks, another physicist on the other side of the world had already seen a hint of antimatter in his equations. A British scientist named Paul Dirac was working on how to describe electrons using both quantum mechanics and the theory of special relativity. Quantum mechanics is the branch of physics that deals with very small scales, like atoms and subatomic particles. Special relativity, developed by Albert Einstein, explains how space and time behave for objects moving at high speeds. Combining these two ideas into one description is not simple. Dirac wanted an equation that could handle both at the same time and still make sense physically. By 1928, Dirac had written down such an equation. It is now called the Dirac equation. and the mathematical object it uses to represent particles like electrons is called a Dirac spinor. The important point for our story is that this equation did not just describe ordinary electrons with negative charge. It also naturally allowed a second kind of solution that behaved like an electron with positive charge. In other words, the math seemed to insist that there should be a partner to the electron, same mass, same kind of spin, but opposite electric charge. At first, this was puzzling. Some people thought these extra solutions might be a sign that the equation was wrong or incomplete, but Dirac took them seriously and suggested that they might represent a real particle that had not yet been found. This was a bold idea at the time. Only later, when Anderson found the positron in cosmic rays, did it become clear that Dirac's mathematical prediction matched something in the real world. In this sense, the theory had pointed to antimatter before the experiment showed it. The electron is not alone in this 2-for-1 pattern. The Standard Model says that many basic particles of matter come in pairs like this. For example, the protons and neutrons in atomic nuclei are not truly fundamental. They are made from even smaller particles called quarks. A proton is built from 3 quarks in a certain combination. A neutron is built from 3 quarks in a slightly different combination. Each type of quark has an antimatter partner called an antiquark. Put antiquarks together in the right way, and you can form antiprotons and antineutrons. These antiprotons and antineutrons can join with positrons, the anti-electrons, to make anti-atoms. In principle, if you had enough of these anti-atoms, you could build larger structures. You could assemble anti-molecules the same way normal molecules are formed, by letting anti-atoms share or trade their outer positrons. Given enough time and the right conditions, whole chunks of solid antimaterial could exist. You could imagine a world built entirely from antimatter, anti-rocks on an anti-surface, under an anti-sky. From far away, such a planet would not look obviously special. Light bouncing off anti-atoms behaves the same way as light bouncing off ordinary atoms. The spectrum of colors it reflects or emits would follow the same rules. If you did not know what it was made of, you might not notice anything strange just by looking at it from space. However, there is a catch. When a particle of matter meets its antimatter partner, they do not simply bounce off each other. They annihilate. Their mass is converted into energy, usually in the form of high-energy light and other particles. This means that a region of space where matter and antimatter are both present in equal amounts would be very violent. The boundary where they meet would glow with intense radiation as particles and antiparticles constantly destroy each other. We do not see large zones like that when we look at space on big scales. The galaxies and clusters we observe do not show the signs we would expect if half of them were made of antimatter and sitting in contact with matter regions. This brings us back to the deep puzzle. The laws of physics, as written in our best theories, mostly treat matter and antimatter in a very symmetric way. If the only real difference between them were the sign of their electric charge, and if the early universe started with matter and antimatter in equal amounts, then it is hard to explain why today's universe seems to be dominated by ordinary matter. This imbalance has a name. It is called the baryonic asymmetry of the universe. Baryonic refers to particles like protons and neutrons, which are in a group called baryons. The asymmetry is the fact that there are many more baryons than antibaryons around us today. To make sense of this, physicists have spent decades searching for any tiny differences in behavior between matter and antimatter that could have been important in the early universe. If, under certain conditions, matter particles and antimatter particles do not behave in exactly the same way, then over a long time, those differences might lead to a universe where matter is left over and antimatter is mostly gone. This idea has guided a long, careful program of research. The goal is simple to state, but hard to reach. Find every way in which matter and antimatter fail to be perfect mirror images of each other. That search continues in modern laboratories. One of the main centers for this work is CERN, the European Organization for Nuclear Research, which operates some of the most powerful particle accelerators in the world. These machines can bring particles to very high energies and smash them together, creating showers of new particles, including antimatter. Special experiments there can produce beams of positrons and antiprotons, slow them down, and trap them using magnetic and electric fields. Once trapped, these antimatter particles and the anti-atoms built from them can be studied in detail. Researchers can measure their properties, such as mass, charge, magnetic moment, and how they respond to forces, and compare those measurements with the same properties for ordinary matter. These comparisons are extremely precise. Physicists look for even tiny mismatches, because a small difference could give a big clue about why the universe favors matter. They also test how antimatter responds to gravity, asking whether anti-atoms fall in Earth's gravitational field in exactly the same way as normal atoms. All of these tests help narrow down which ideas about the early universe are possible and which are not. But before turning to the details of those experiments and what they have found, it is helpful to pause and collect what is already known about the basic properties of antimatter. When scientists study antiparticles one by one, away from everything else, they measure their built-in properties very carefully. Over many years, with better and better instruments, they have checked things like mass and charge again and again. The result is clear. An antiparticle has exactly the same mass as its matching particle of ordinary matter. An anti-electron and an electron weigh the same. An antiproton and a proton weigh the same. When they move through electric and magnetic fields, they also respond in the same way as their ordinary partners, except that the direction of the force is reversed because their electric charge has the opposite sign. This is exactly the kind of behavior Carl Anderson first saw in his cloud chamber tracks. But electromagnetism is only one piece of the bigger picture. In modern physics, we talk about four fundamental forces that shape how particles move and interact: gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Electromagnetism handles electric charges and light. The strong force holds the centers of atoms together. The weak force is involved in certain kinds of radioactive decay. Gravity pulls mass toward mass. For a long time, it seemed that matter and antimatter might be almost perfectly symmetric under all of these forces, except for the sign of the electric charge. That idea began to change when physicists studied the weak force more deeply in the 1950s and 1960s. As they explored weak interactions, they discovered that this force behaves in a very special way. It cares about something called handedness or chirality. This is not an everyday idea, and it is tricky to picture for particles that have mass. But we can use a rough comparison to something called helicity. Helicity tells you how a particle's spin is oriented relative to the direction it is moving. If the spin points along the direction of motion, we call that right-handed. If the spin points opposite the direction of motion, we call that left-handed. Real particles with mass can switch between these states in some situations. So the analogy is not perfect, but it gives an intuitive picture. With that picture in mind, the weak force shows a very unusual preference. Ordinary matter particles only feel the weak force if they are left-handed. Antiparticles only feel the weak force if they are right-handed. Right-handed electrons do not participate in weak interactions in the usual way, while left-handed electrons do. Right-handed neutrinos, if they exist at all, seem to be invisible to the weak force, while left-handed neutrinos are active. The same kind of rule holds for antiparticles, but flipped. This kind of one-sided behavior does not appear in electromagnetism or gravity, and it was a major surprise. There was another layer to that surprise. When experiments compared how strongly the weak force acted on left-handed particles and on right-handed antiparticles, they found that the strengths were not simply mirror images of each other. There were small but real differences in the probabilities of certain processes. In practice, this means that when a nucleus undergoes radioactive decay through the weak force, the chance of a particular decay path is slightly different from the chance for the matching process in an antinucleus made from antimatter. The pattern of outcomes for matter and antimatter is not exactly the same. This fundamental imbalance was first seen in detail in an experiment in 1963, carried out by James Cronin and Val Fitch at Princeton University. They studied the decays of particles called kaons and noticed that the behavior of these particles did not match perfectly with the behavior of their antiparticle partners. The symmetry that would normally make matter and antimatter look like perfect mirror images in these weak processes was broken. For uncovering this effect, they were awarded the Nobel Prize in Physics. Their results showed that the weak force draws a slight but important distinction between matter and antimatter. When this difference was confirmed, many physicists hoped they had finally found the key to the baryonic asymmetry of the universe, the puzzle of why there is so much more matter than antimatter on large scales. If the weak force treats particles and antiparticles differently, then in the hot, dense, early universe, these small differences might have built up over time. Perhaps they could have favored matter just enough that, after matter and antimatter mostly annihilated each other, a small excess of ordinary matter would remain to form stars, planets, and us. However, when theorists worked through the detailed calculations, the numbers did not cooperate. The amount of asymmetry produced by the known differences in weak interactions, while real and measurable in experiments, was not large enough to explain the huge imbalance we see today. The weak force's preference for one kind of handedness and its slightly different treatment of particles and antiparticles was an important clue, but it was not the whole answer. So, the search continued. Attention then shifted to the strong nuclear force, the interaction that binds quarks together inside protons and neutrons and keeps atomic nuclei from flying apart. Theories of the strong force suggested that it might also allow for subtle differences between left-handed and right-handed particles, and between matter and antimatter. If such differences existed, they could, in principle, create additional asymmetries that might add up to the matter-dominated universe we see. But once again, antimatter did not behave in the way some models had hinted it might. As experiments grew more precise, they repeatedly showed that the strong interaction seems to treat particles and antiparticles in the same way, at least within the very tight limits of our measurements. No clear violation of the expected symmetry has been seen in the strong force so far. In that sense, antimatter turned out to be too well behaved under the strong interaction, offering no obvious new handle on the cosmic imbalance. This path of investigation brought physicists to the last of the four fundamental forces: gravity. Gravity is the force that keeps your feet on the ground, holds planets in orbit around stars, and binds galaxies together. The idea that gravity might act differently on antimatter than on matter is considered a long shot by many scientists, because everything we know about gravity from centuries of observation points to a very simple rule. All objects fall the same way in a given gravitational field, regardless of what they are made of. A famous story, often used to illustrate this idea, involves Galileo and the Leaning Tower of Pisa. According to the legend, he dropped stones of different sizes and materials from the top of the tower and found that they hit the ground at nearly the same time. In modern language, we say that in Earth's gravitational field, all freely falling objects near the surface accelerate downward at about 9.8 meters per second squared, as long as we ignore air resistance. A light ball and a heavy ball dropped in a vacuum will fall side by side. In the 17th century, Isaac Newton took this idea and turned it into a quantitative theory. He showed that the gravitational acceleration you feel depends on how massive the object pulling you is and how far away you are from its center. It does not depend on what you are made of, or whether you are a stone, a feather, or a ball of metal. In fact, if you are in free fall, your own mass cancels out of the equations. This property, that gravitational motion does not depend on the internal makeup of the falling body, is closely related to what we call the equivalence principle. The equivalence principle later became one of the cornerstones of Albert Einstein's theory of general relativity, which is still our most successful description of gravity. In general relativity, gravity is not treated as a simple force pulling along a line. Instead, mass and energy curve space and time, and objects follow paths in this curved space-time. The idea that all objects, regardless of their detailed structure, fall along the same kinds of paths is deeply built into the theory. Because of this, most physicists expect that antimatter should fall just like matter in a gravitational field. Even so, physics is, at its heart, an experimental science. Theoretical expectations, no matter how convincing, are not enough by themselves. Until you actually test how antimatter behaves in a gravitational field, you cannot be completely sure that it obeys the same rules as ordinary matter. The universe has surprised us before, so a group of physicists at CERN decided to take on the challenge of measuring, directly and carefully, how antimatter responds to Earth's gravity. Their motivation came from more than one direction. The baryonic asymmetry of the universe is still an open question, and some researchers have suggested that small differences in gravitational behavior between matter and antimatter might contribute to the answer. In addition, a few speculative ideas about dark matter and dark energy, the unknown components that seem to dominate the large-scale behavior of the universe, hinted that if antimatter had an unusual kind of gravitational charge, it could help explain some puzzling cosmic observations. In some of these models, antimatter might even be repelled by ordinary matter's gravity, which would mean that, in a sense, antimatter would fall up instead of down. These ideas are bold and not part of standard theory, but they are testable. To explore them, CERN hosts several specialized experiments that focus on the gravitational properties of antimatter. Among them are projects with names like AEGIS, G-BAR, and ALPHA. Each experiment uses different techniques to create, trap, and observe antimatter, but they all share the same central goal: to see whether antimatter in free fall accelerates in exactly the same way as matter near Earth's surface. One of the most closely watched efforts comes from the ALPHA collaboration. Their work recently led to a high-profile result published in the scientific journal Nature in late September of a recent year. For decades, people had simply assumed that antimatter would follow the same gravitational rules as ordinary matter, because every other test of equivalence had come out that way. The ALPHA experiment changed the conversation by providing direct measurements of the gravitational acceleration of antihydrogen, an atom made from an antiproton and a positron close to Earth. Before looking at the numbers, it is worth pausing to appreciate how delicate this kind of measurement is. Gravity is actually the weakest of the four fundamental forces at the scale of individual particles. Tiny electric or magnetic fields, small temperature changes, or even stray vibrations can easily overwhelm the gentle pull of gravity on a single anti-atom. To isolate the gravitational effect, the experimenters had to design an intricate setup that shields antimatter from other influences and lets it move freely enough for gravity to show its effect in a measurable way. The first step in this process is to create and control a supply of antimatter. For the alpha experiment, that starts with a beam of positrons, anti-electrons, coming from a radioactive source. A particular isotope of sodium is chosen because, as it decays, it emits positrons at a steady rate, sending out several million of them every second. These positrons are directed into the experimental apparatus, where fields and materials are arranged to slow them down and guide them. Most of these positrons never make it into stable anti-atoms. Instead, as they move through the setup, they encounter ordinary matter in the walls, gas, or other parts of the equipment. When a positron meets an electron from ordinary matter, the two particles annihilate each other. In that event, their mass is converted into energy, according to Einstein's famous relation, and the energy is released as high-energy light. Detectors around the experiment can see these annihilations as small flashes, each one marking a tiny burst of energy carried away in the form of light. Only a small fraction of the positrons manage to survive as they pass through the first stages of the experimental setup. Most are lost in annihilations with ordinary matter, but a tiny remainder is carefully guided forward. These surviving positrons are slowed down by passing through low-pressure gases, which act a bit like a gentle brake, taking away some of their energy without destroying them. At the same time, electric and magnetic fields are arranged to trap them in a controlled region of space, keeping the cloud of positrons confined so that the experimenters can decide what happens next. Even with all this control, trying to watch the pull of gravity on these positrons alone would be nearly impossible. Their masses are so small that the gravitational force on each particle is extremely weak. Any slight change in the surrounding electromagnetic fields, even tiny fluctuations that are hard to avoid, would easily drown out the effect of gravity. To get around this problem, the experiment takes advantage of the fact that neutral atoms are much less sensitive to stray electric fields. The collection of positrons is merged with a separate supply of antiprotons stored in a different part of the apparatus. When an antiproton and a positron meet under the right conditions, they can bind together, forming an anti-atom called antihydrogen. Antihydrogen is the antimatter version of the simplest atom, hydrogen, which, in ordinary matter, is made from one proton and one electron. In antihydrogen, the roles are reversed. One antiproton at the center, one positron orbiting it. Because the charges of the antiproton and the positron cancel overall, the antihydrogen atom is electrically neutral. That neutrality makes it far less responsive to small electric fields in the environment. The antiprotons themselves are created earlier in the process using a high-energy accelerator. In simple terms, a beam of ordinary protons is fired at a block of dense material at very high speeds. The collisions are so energetic that they briefly create sprays of new particles, including antiprotons. These antiprotons are then separated out, slowed down, and stored using electromagnetic traps. By the time they are brought together with the positrons, both ingredients are under good control. The merger of the two trapped clouds, positrons and antiprotons, produces a population of antihydrogen atoms that can be used to probe gravity. Once formed, each antihydrogen atom acts like a very small magnet. This is because the positron inside has a property called spin and a tiny magnetic moment, and the antiproton contributes as well. When placed in a carefully designed magnetic field, these magnetic moments allow the anti-atoms to be held in place. The ALPHA setup uses a complex arrangement of magnets to create a kind of magnetic bottle. In this bottle, the magnetic field is stronger near the edges and weaker in the middle, so the antihydrogen atoms tend to stay in the central region, where the effective magnetic potential is lowest. The magnetic interaction is still present, but it is weak enough that it no longer completely hides the much smaller effect of gravity that the experiment is trying to measure. The chamber that holds the antihydrogen is pumped down to a very high vacuum. To get a sense of how empty it is, there are only about 200,000 atoms of ordinary gas in each cubic centimeter of the chamber. For comparison, at typical atmospheric pressure near Earth's surface, there are on the order of 20 quintillion gas atoms in each cubic centimeter. That means the density inside the experiment is lower by a factor of roughly 100 trillion. Under these near-vacuum conditions, the trapped antihydrogen atoms almost never bump into ordinary atoms. Collisions that would lead to annihilation and bursts of energy are rare. Instead, the anti-atoms can drift, bounce, and move within the magnetic bottle for many seconds, sometimes even for minutes, without being disturbed. With the antihydrogen prepared and gently held, the researchers can move on to the main test. The key idea is to let gravity compete with the magnetic trapping forces in a controlled way. The magnets are arranged so that they provide vertical confinement. They help keep the anti-atoms from drifting upward or downward out of the trap. In the measurement phase, the strength of these vertical magnetic fields is gradually reduced. As the trapping fields weaken, the antihydrogen atoms are no longer held as tightly. They continue to move randomly because of their small leftover energies, and eventually some of them reach the top or bottom boundaries of the trap region. When an antihydrogen atom reaches such a boundary, it encounters the material walls of the apparatus. There, it meets ordinary matter atoms and annihilates. The antiproton and the positron disappear in a burst of energy, mainly in the form of high-energy light and other particles. Sensitive detectors around the chamber record these events as sharp signals at specific positions. By tracking where and when these annihilations occur, the experimenters can build up a map of how many anti-atoms escape through the bottom of the trap versus how many escape through the top. In the alpha experiment, this release phase, during which the trap fields are ramped down and the atoms are allowed to escape, lasts for about 20 seconds. The logic behind the measurement is straightforward, even though the setup is complex. If gravity pulls antihydrogen downward in the same way it pulls ordinary hydrogen, then, during the release, more anti-atoms should drift down and escape through the bottom of the chamber. If gravity somehow pulls antihydrogen upward, the opposite would happen. More anti-atoms would escape through the top. If gravity did not act on antihydrogen at all, then the only effects would come from the weakening magnetic fields and the random motion of the atoms. In that case, the numbers escaping from the top and bottom would be closer to balanced, with any difference coming mainly from small asymmetries in the trap. To make these expectations precise, the ALPHA team ran detailed computer simulations of how antihydrogen atoms would move in their apparatus under different assumptions. In the scenario where gravity pulls downward with the familiar strength of 1g, 1 Earth gravity, The simulations showed that about 85% of the escaping antihydrogen should leave through the bottom. If, instead, gravity pulled upward with the same strength so that antihydrogen effectively fell up, then only about 20% of the atoms would be expected to escape from the bottom. A third case considered no gravitational force on antihydrogen at all. In that situation, the simulations gave a more even split, with about 55% of the atoms leaving through the bottom and the rest through the top. The slight excess over a perfect 50-50 split comes from tiny imperfections in the real magnetic fields and geometry of the device. When the actual experiment was carried out, the observed pattern landed clearly in one of these broad categories. Roughly 75% of the antihydrogen atoms were seen to escape through the bottom of the chamber during the release phase. This is much closer to the falls down case than to either the falls up or no gravity cases. The data show a definite preference for downward motion under Earth's gravity. In other words, at least on this first pass, antihydrogen seems to be pulled down rather than pushed up or left unaffected. As careful scientists, the ALPHA team did not stop after a single run. They repeated the procedure many times, collecting a set of measurements under slightly different conditions. One important variation involved adjusting an additional magnetic bias field that could push the anti-atoms upward or downward. This bias acts like an extra force on top of gravity. In their analysis, they label these settings in terms of G. A bias of -1 G means that the magnetic forces are tuned to provide an upward push just strong enough to cancel normal gravity. A bias of +1 G means that the magnets add an extra downward push equal in strength to gravity, effectively doubling the total downward acceleration. Other bias values shift the balance in smaller ways. For each bias setting, the team used simulations to predict how many antihydrogen atoms should escape through the bottom under different possible gravitational behaviors. Each scenario, normal downward gravity, zero gravity, or upward gravity, produces its own curve when you plot the escape fraction as a function of bias. In the published results, these curves are shown in different colors, such as orange, green, and purple, to distinguish them. The actual measurements appear as blue data points, with vertical lines showing the uncertainty in each point. By comparing where the blue points fall relative to the curves, the researchers can see which gravitational scenario is most compatible with the data. The outcome is that the blue points line up best with the curve that represents normal downward gravity on antimatter. That is the orange case in the reported figure. The points do not sit exactly on the curve, but they follow its trend much better than they match the curves for zero gravity or upward gravity. When the team fits the data quantitatively, they find that the best estimate for the gravitational acceleration of antihydrogen is about 0.75 G, meaning about 3/4 of the acceleration experienced by ordinary matter at Earth's surface. At first glance, this might sound like a sign that gravity acts differently on matter and antimatter. If antihydrogen really fell with only 75% of the usual acceleration, that would be a major discovery. However, before drawing that conclusion, it is necessary to look carefully at the uncertainties in the measurement. Each data point has an associated error bar, reflecting both random variations and systematic effects. There are uncertainties in how accurately the magnetic bias was set and measured, as well as possible small misalignments of the apparatus. There are also statistical uncertainties due to the limited number of antihydrogen atoms observed. When all these sources of uncertainty are combined, the final reported result is written as 0.75 G plus or minus 0.13 G plus or minus 1.6 G. The first plus or minus term reflects statistical uncertainty, while the second reflects systematic uncertainty. The large systematic term means that, within the present precision, a full 1 g of gravitational acceleration for antihydrogen is still quite compatible with the data. In other words, although the central value of the fit is below 1 g, the range of values allowed by the error bars comfortably includes 1 g. What the experiment clearly rules out are the more extreme possibilities, such as antimatter experiencing a strong negative gravitational charge and falling upward with ordinary gravity strength. Future measurements, with improved control of systematics and larger samples of antihydrogen, will tighten these bounds and may bring the central value closer to 1 g or reveal a small deviation. For now, though, the main message is already important. Antimatter does not float freely or race upward in Earth's gravitational field. It falls in the same general direction as ordinary matter. When we put this result together with what is known about electromagnetism and the strong force, a pattern emerges. Despite all the strange and counterintuitive features of antimatter, it appears that, so far, only the weak nuclear force treats particles and antiparticles in a truly different way. The differences that have been measured so far between matter and antimatter are subtle. They show up in the weak nuclear force as small shifts in probabilities, and they are important clues. But to fully explain why the universe today is filled with ordinary matter and almost no antimatter, those small differences do not seem to be enough. The imbalance between the two is huge. To account for it, nature would likely need to treat matter and antimatter much more unevenly than our current measurements suggest. That is why the puzzle of the matter-antimatter asymmetry is still open, and why scientists are not ready to stop searching. One possible path forward is the idea that there may be forces we have not discovered yet, or particles that do not fit into the standard model. These new ingredients, if they exist, might interact with antimatter in a more dramatic way, tipping the balance in the very early universe. Another possibility is that there are rare processes, not yet seen in experiments, where matter and antimatter behave very differently. Some researchers even ask whether we might have to live with the idea that the imbalance is simply a result of the way conditions unfolded after the Big Bang, without a deeper rule behind it. For many physicists, that last option feels unsatisfying. They prefer to believe that such a large feature of the universe should have a clear physical cause, even if we have not found it yet. As questions about antimatter continue, other strange pieces of the subatomic world also draw attention. To learn about them, scientists need tools that can reach far beyond the limits of our senses. One of the most important tools is the telescope. But the word telescope can mean very different things depending on what you are trying to observe. When people hear it, some picture a long, narrow tube made of wood or brass, with lenses at both ends, like the kind used by Galileo centuries ago to look at the moons of Jupiter. That simple design, with glass-bending, visible light, opened a new window on the sky. Others might think of the huge observatories that sit on dry, high mountain tops in places like Chile or Hawaii. There, giant mirrors, as wide as a tennis court, collect faint light from distant galaxies and nebulae. These mirrors are protected by great white domes that slowly rotate to follow the stars as Earth turns. Inside, delicate instruments measure how bright the light is and how its colors are spread out, revealing the temperature, motion, and chemical makeup of objects that are many millions of light years away. Some people may also imagine large radio dishes, shaped like shallow bowls, that listen for radio waves instead of collecting visible light. Famous instruments like the now collapsed Arecibo telescope in Puerto Rico once used a huge fixed dish built into a natural valley with a movable receiver hanging above it. These radio telescopes search the sky for signals from pulsars, gas clouds, and even distant galaxies, turning invisible radio waves into information we can study. All of these are telescopes in the sense that they collect and focus some kind of signal from space. But there is another kind of telescope that looks nothing like a tube, a dome, or a dish. If you could see it from above, it would not stand out on the landscape at all, because it is hidden deep underground. It is a telescope made from a cubic kilometer of clear, ancient ice at Earth's South Pole. Buried below the frozen surface of Antarctica, this detector watches for one of the most elusive types of particles known, the neutrino. From the surface, the area looks like a harsh, flat field of snow and ice, swept by cold winds and lit by a low sun that circles the horizon for months. The facility nearby, the Amundsen Scott South Pole Station, is the southernmost permanent research base on the planet. It is a place of extreme cold, long polar nights, and isolation. Underneath this remote outpost, strings of light sensors are frozen into the ice, forming a three-dimensional grid that stretches down for more than a kilometer. This is the IceCube Neutrino Observatory. It uses the ice itself as part of the detector, turning the frozen water into a transparent medium where rare particle events can be seen. The idea of building such an instrument in this extreme environment might seem odd at first. Why go to the South Pole? And why drill deep holes in the ice just to study tiny particles? The answer lies in the nature of the neutrino. Neutrinos are fundamental particles in the same broad category as electrons and quarks. They are not made from anything smaller, as far as we know. Many neutrinos that pass through Earth come from the sun, produced in the nuclear fusion reactions at its core. In those reactions, light elements are forced together to form heavier ones, releasing energy and, as a side effect, streams of neutrinos. Other neutrinos are born in much more violent places, when a massive star explodes as a supernova, or when matter spirals into a supermassive black hole at the center of a galaxy. The energies involved are extreme. These events can accelerate particles to very high speeds and break apart atoms into their basic components. In those chaotic conditions, neutrinos are produced in great numbers and sent flying off into space in all directions. Some of them eventually reach our planet after traveling across vast distances. Within the family of particles, neutrinos are grouped with electrons in a set called leptons. One feature that leptons share is that they do not feel the strong nuclear force, the force that binds quarks together inside protons and neutrons and holds atomic nuclei together. Electrons do feel the electromagnetic force because they carry electric charge. Neutrinos, however, are electrically neutral. They carry no electric charge and, as far as we can tell, have only a tiny amount of mass. These two properties, no charge and extremely small mass, mean that neutrinos interact with other matter only through the weak nuclear force and gravity. Gravity is far too weak at the particle scale to matter much, so the weak force is the only significant way neutrinos can interact. Because the weak nuclear force acts over very short distances and is much less strong than electromagnetism or the strong force at everyday energies, neutrinos barely notice the matter they pass through. Most of the time, they simply continue in straight lines, as if the atoms in their path were not there at all. This is what gives them their ghost-like reputation. They are sometimes called ghost particles because they seem to move through solid matter as though it were almost transparent. This tendency to ignore matter is the same property that makes neutrinos so hard to detect. Even when scientists do manage to see signs of them, They do not see the neutrinos directly. Instead, they see the results of rare interactions in which a neutrino happens to collide with another particle inside a detector. When such a collision occurs, it can knock loose a charged particle, such as an electron or a muon, which then moves through the detector medium. That charged particle can create a flash of light or some other signal that sensors can record. By studying the direction, energy, and timing of these secondary signals, researchers can infer that a neutrino passed through and interacted. To understand just how elusive neutrinos are, it helps to think about what happens as they pass through Earth. A typical neutrino can travel through the entire planet from one side to the other without interacting even once. It can cross the crust, mantle, and core without changing direction, almost never striking an atomic nucleus or an electron in a way that leaves a trace. From the neutrino's perspective, Earth is mostly empty space. The numbers involved are almost beyond everyday experience. At any moment, there are enormous numbers of neutrinos flying through your body. Many of them come from the sun. Others come from distant cosmic events. The total is measured in trillions every second. Yet, because neutrinos interact so rarely, the chance that even one of these particles will collide with an atom in your body during your entire lifetime is very small. Roughly speaking, the odds are about 1 in 4 that a single neutrino will interact with one of your atoms over all the years you are alive. Neutrinos like to ignore almost everything, and the sun gives us a clear example of just how strongly they refuse to interact with matter. Deep in the sun's core, nuclear fusion reactions create both photons, which are particles of light, and neutrinos. The photons do not get out easily. Each photon is absorbed by atoms in the hot plasma, then re-emitted in a random direction, then absorbed again. It is like taking one step forward and many steps sideways, over and over. Because of this endless zigzag, a photon can take around 1 million years to make its slow journey from the center of the sun to its surface, where it finally escapes into space as sunlight. Neutrinos born in those same fusion reactions have a very different story. They barely notice the atoms in the sun at all. Instead of being absorbed and re-emitted, a typical neutrino simply flies straight outward, passing through the dense solar material as if it were mostly empty. Traveling at almost the speed of light in a vacuum, a neutrino produced in the core of the sun can leave the sun's interior in about 2 seconds. While photons wander, neutrinos go almost straight. Among all the particles in the Standard Model, neutrinos are some of the most reserved. They rarely interact, they carry no electric charge, and they slip through matter without leaving a trace most of the time. Yet, every once in a while, a neutrino does collide with an atomic nucleus or an electron. When that happens, the interaction can set off a chain of energetic events, sending new particles flying outward. It is this rare but dramatic cascade that the IceCube detector is built to catch. At first glance, the IceCube Observatory might not look like a telescope at all, but in a broad sense, it is. It does not have mirrors or lenses. Instead, it uses thousands of light sensors buried deep under the Antarctic ice. There are 5,160 of these sensors, called digital optical modules, or DOMs. They are arranged on long cables that hang down between about 1.5 kilometers and 2.5 kilometers beneath the surface of the ice. Down at those depths, the ice is dark and clear. Sunlight from above has been completely blocked by the thick layer of frozen water on top, but that does not mean there is no light at all down there. Cosmic rays and neutrinos can pass into the ice from above, below, or from the side. When one of these high-energy particles happens to collide with a nucleus in the ice, the collision can create new particles, including muons. Muons are heavier cousins of the electron. They carry electric charge and move quickly when they are produced in these interactions. In IceCube, muons are especially important because they act as tracers. If a neutrino interacts and makes a muon, the muon's path and the light it produces can give information about the neutrino's direction and energy. As a muon rushes through the ice, something interesting can happen. Inside a material like ice, light does not travel as fast as it does in empty space. The speed of light in a vacuum is the ultimate speed limit in the universe, and nothing with mass can go faster than that. But when light moves through a medium such as glass, liquid water, or solid ice, it slows down. A muon, on the other hand, can travel through the ice at a speed that is less than the vacuum speed of light, but still greater than the speed at which light moves in that ice. In that special situation, the muon is not breaking the cosmic speed limit, but it is outrunning the light waves that would normally move through the same material. When a charged particle, like a muon, moves through a medium faster than light can move through that medium, it creates a kind of electromagnetic shock wave. This shock wave takes the form of a cone of blue light spreading out from the particle's path. The effect is known as Cherenkov radiation. In many images of nuclear reactors, you can see a glowing blue light in the water around the reactor core. That glow is Cherenkov radiation produced by fast-moving charged particles in the water. The same basic process happens in the Antarctic ice when a muon speeds through it. Cherenkov radiation is sometimes compared to a sonic boom, but in the language of light instead of sound. To understand the analogy, it helps to think about how a sonic boom is made. When a jet plane moves through the air at ordinary speeds, it creates pressure waves that travel outward in all directions. Those waves are simply sound. As the plane's speed gets closer to the speed of sound in air, the sound waves in front of the plane start to pile up because the plane is nearly keeping up with them. This buildup creates a high-pressure front. Once the plane exceeds the speed of sound, it breaks through that front, and the pressure changes suddenly. The result is the loud, sharp sound we call a sonic boom. The shock front then spreads out behind the plane in a cone-shaped pattern. In the case of Cherenkov radiation, the medium is not air but ice or water, and the waves are not sound waves but light waves. The muon is like the jet plane. As it moves faster than light can travel through the ice, the electric field of the muon disturbs the atoms of the medium. More precisely, its electric charge interacts with the electrons in the water molecules, shifting them slightly and polarizing them. These disturbed molecules try to follow the changing electric field of the passing muon, but cannot respond instantly. Their responses pile up in a way that is similar in spirit to sound waves building up in front of a fast jet. As the water molecules relax back to their usual unpolarized state, they release energy that was stored in the distortion of their electric fields. That energy is emitted as photons, mostly in the blue part of the spectrum. The photons are not sent out randomly. They form a cone-shaped wavefront, set by the speed of the muon and the speed of light in the ice. To an observer with sensitive instruments, this appears as a ring or streak of blue light, depending on the viewing angle. This is Cherenkov radiation, the optical boom produced when a charged particle outruns the local light speed in a material. Inside IceCube, each digital optical module is a light detector waiting for these faint signals. When a muon passes near one of the modules and produces Cherenkov radiation, some of the blue photons reach the detector, triggering it. By recording the time and brightness of the signals in many detectors, scientists can reconstruct the path of the muon. From the shape and direction of that path, they can then infer where the original neutrino came from and how much energy it likely carried. The key point is that all of this light comes from a chain that starts with a neutrino interaction and continues through the motion of the muon. The muon is not pushing air the way a jet does, but it is disturbing the electric fields within the ice through its charge. The passing muon polarizes the water molecules along its route, nudging their electrons into slightly shifted positions. As each molecule settles back to its normal state, it gives off a little bit of light. These countless small emissions add up to the continuous cone of Cherenkov radiation. This is happening all along the path the muon takes through the ice. As a muon travels through the Antarctic ice, it keeps disturbing the water molecules along its path. Each disturbance sets off tiny ripples in the electromagnetic fields around those molecules. The molecules respond by emitting little pulses of light that spread outward. Because the muon is moving in a definite direction, these ripples are not just random. Taken together, they form a cone of light that points roughly along the direction in which the muon is moving. The pattern is structured, not chaotic, and its shape carries information about the particle that created it. If the muon were traveling more slowly than light moves through the ice, the picture would be very different. Each tiny pulse of light would expand outward like a small sphere centered on the point where it was emitted. These expanding spheres would overlap in complicated ways. At most places, the light waves would cancel one another out through destructive interference. Because their peaks and valleys would not line up, on average, there would be no sharp wavefront, no clear buildup of light in any one direction, and no strong, coherent glow. The net effect would be close to darkness. What makes Cherenkov radiation special is that the muon is moving faster than light can travel in that medium, while still staying below the universal speed limit of light in a vacuum. In that situation, the light waves cannot spread out evenly. They are forced into a specific cone-shaped shock front, where many waves add together in phase. This constructive interference produces a visible flash of blue light that marks the muon's route. The blue color appears because shorter wavelengths are favored in this process in ice and water, so the radiation peaks in the blue and ultraviolet range of the spectrum. The IceCube Observatory is designed to watch for this signature blue glow. Its thousands of digital optical modules, or DOMs, are always ready to record the tiny bursts of Cherenkov light that pass through the ice. Each time a DOM detects a flash, it records the exact moment it happened. The differences between the detection times and neighboring modules are incredibly small, but they are crucial. By comparing when each DOM in the array saw the light, scientists can reconstruct the path of the muon that produced it. This timing information works a bit like listening to echoes in a canyon. If you know where your microphones are, and when each one hears the echo, you can figure out where the original sound came from. In IceCube, the DOMs are the microphones, and the Cherenkov light is the echo. Using the full three-dimensional pattern of detection times and brightnesses, researchers can trace the muon's path back through the ice. From that reconstructed track, they can infer the direction and energy of the incoming neutrino that set the whole chain of events in motion, and they can point back out into space toward its likely origin. Each DOM is a carefully engineered instrument, built to operate for years in one of the harshest environments on Earth. From the outside, a DOM looks like a smooth, clear sphere. The sphere is made of thick glass, about the size of a 13-inch ball, strong enough to withstand the high pressure at depths of more than a kilometer and the extreme cold of Antarctic ice. The glass shell keeps the delicate electronics inside dry and stable even as the ice slowly compacts around it over time. Inside the glass sphere, the main active component is a photomultiplier tube. This device is sensitive enough to notice even a single photon of light. When a photon from a Cherenkov flash reaches the photomultiplier surface, it can knock loose an electron. That electron is then accelerated and multiplied through a series of internal stages, creating a much larger electric signal from a very small amount of light. Additional electronics inside the dome shape amplify and digitize this signal, turning it into data that records the time and strength of the detected flash. Cables running up from each dome carry both power and data. The recorded signals are sent upward through the ice to the surface station, where they are collected by computers. Because there are more than 5,000 DOMs, the total amount of data generated is enormous. IceCube captures about 1 terabyte of measurements every day. That is roughly the same as storing the text of millions of pages daily. Of that data, hundreds of gigabytes are transmitted by satellite links to research groups around the world. Teams of scientists then analyze the information, looking for the subtle patterns that indicate neutrino events. Hidden within this constant flow of numbers are the footprints of many different kinds of particles that reach the detector from outside Earth's atmosphere. The overwhelming majority of these events come from cosmic rays. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that strike the upper atmosphere and create showers of secondary particles. IceCube detects on the order of 275 million such cosmic ray-induced events every day. These signals are scientifically valuable in their own right, but for researchers focused on neutrinos, they act mostly as a thick curtain of background noise. Against this noisy backdrop, neutrino interactions are much rarer. IceCube sees only about 275 neutrino-related events per day that stand out clearly enough to analyze. That is about 1 million times fewer than the number of cosmic ray events. Over the course of a year, the observatory collects data from roughly 100,000 neutrino detections. However, almost all of these neutrinos are not from far-off galaxies. They are produced in Earth's own atmosphere, when cosmic rays collide with atoms in the air, creating unstable particles that then decay and emit neutrinos as byproducts. These atmospheric neutrinos are useful for studying particle physics and testing models of how neutrinos change type as they travel, but they do not directly tell us about distant cosmic engines. For that, scientists need to pick out the much scarcer neutrinos that originated in powerful astrophysical sources beyond our planet. The key word is almost. Among the many atmospheric events, a small fraction of detections come from genuine cosmic neutrinos, with energies and directions that point back to dramatic processes far out in the universe. On the 22nd of September in the year 2017, IceCube recorded one such remarkable event. The array registered an unusually bright and energetic burst of Cherenkov light deep in the ice. Many DOMs lit up in quick succession, mapping out a long, clear track of a very high-energy muon. By working together, the detectors used the tiny differences in their detection times to reconstruct the muon's path with high precision. When the team traced that path backward through Earth and out into the sky, they found that it pointed toward a known active galaxy. Further observations by telescopes operating at other wavelengths, including gamma rays and X-rays, showed that this galaxy was in a flaring state, emitting strong jets of radiation. At its center lies a supermassive black hole, feeding on surrounding matter and launching narrow beams of high-energy particles in opposite directions. Because one of those jets happens to be oriented roughly toward Earth, this kind of object is called a blazar. The connection between the neutrino detected by IceCube and the flaring blazar was a major result. It provided evidence that at least some of the highest energy neutrinos observed on Earth are produced in the extreme environments around supermassive black holes. This was a key step in the growing field of multi-messenger astronomy, in which information from neutrinos, light, and other signals are combined to study the same cosmic event. Still, this was not the first time that IceCube had seen neutrinos from far beyond our own atmosphere. It was not the first time that IceCube had detected neutrinos from deep, deep space. This particular detection stood out not only because of its high energy, but because of what happened next. For the first time, IceCube issued a real-time alert to observatories around the world, signaling that something unusual and important was happening in a specific patch of sky. Within minutes, telescopes using radio waves, visible light, X-rays, and gamma rays began to turn toward that direction. The event marked IceCube's full entry into what is now called multi-messenger astronomy, a way of studying the universe that combines different kinds of signals: light in all its forms, gravitational waves, cosmic rays, and neutrinos. For most of the history of astronomy, our view of the cosmos has relied on light alone. We have built tools to see it across many wavelengths, from low-energy radio waves to high-energy gamma rays. But at the end of the day, everything depended on photons. In recent years, new messengers have joined that picture. Gravitational wave detectors, such as those that first recorded the merging of neutron stars, have opened up a way to listen to ripples in space-time itself. Neutrino observatories like IceCube add yet another kind of information, one that complements both light and gravitational waves. Neutrinos are especially valuable for this task because, like gravitational waves, they can escape from places that are hard or even impossible for light to leave quickly. In a dense, hot explosion, light can be trapped, scattered, or absorbed many times before it finds a way out. Dust, gas, magnetic fields, and dense plasma can all slow and distort the photon's journey. Neutrinos, by contrast, interact so weakly that they tend to fly straight through such regions. They take a more direct path from the heart of the event to our detectors. That means they can reach us earlier or carry information from deeper inside. IceCube is now part of a coordinated global system of observatories that share alerts and data. When its detectors register a neutrino that looks likely to have come from a distant astrophysical source, automated systems can send out messages that include an estimate of the neutrino's energy and the direction it came from. Radio arrays, optical telescopes, X-ray satellites, and gamma-ray observatories can then point their instruments toward that location. Together, these different instruments can follow up on short-lived, high-energy events that might otherwise go unnoticed. This networked approach makes IceCube an important early warning system. It does not replace traditional telescopes, but it guides them. In doing so, it gives us a chance to study brief cosmic outbursts in much more detail than any one type of detector could manage alone. Neutrinos add another layer of information about the processes that drive jets from black holes, the collapse of massive stars, and the collisions of compact objects, such as neutron stars. Because neutrinos can pass almost unhindered through extremely dense and hot regions, they offer a view into the inner workings of astrophysical engines. In a core collapse supernova, for example, most of the energy is carried away by neutrinos, not by light. In the merger of two neutron stars, the dense matter and strong magnetic fields make photon signals complex and delayed, while neutrinos may escape more directly. Even near a supermassive black hole, where matter spirals inward and fields twist violently, neutrinos can give clues about the highest energy particle accelerators nature has to offer. The particles that produce these neutrino signals reach energies far beyond what we can generate in laboratories on Earth. Even the most powerful human-made accelerators, such as those at CERN, fall short of the energies involved in cosmic jets and explosions by many orders of magnitude. By studying neutrinos that arrive from these distant sources, physicists can test their theories under conditions that cannot be recreated in terrestrial experiments. This includes theories about how particles interact at extreme energies, how cosmic rays are produced and accelerated, and how matter behaves when it is compressed to densities beyond those found in atomic nuclei. The information from IceCube does not only help us understand neutrinos themselves, it also feeds into broader questions about the universe. Some models of dark matter predict that dark matter particles could decay or annihilate in ways that produce high-energy neutrinos. By measuring the spectrum and arrival directions of neutrinos, IceCube can place limits on these models, or hint at preferred possibilities. The observatory has even been used to study properties of the Antarctic ice, since the clarity and scattering of light in the ice affect how Cherenkov radiation is recorded. None of this would be possible without the long and difficult effort that went into building the detector. Constructing IceCube required years of planning and 7 seasons of fieldwork. The project could only move forward during the Antarctic summer months from November to February, when conditions allow aircraft to reach the South Pole. During the long, dark winter, when temperatures plunge and storms cut off access, construction had to pause. Equipment and supplies could not be flown in, and crews had to work with what was already on site. Over those 7 years, the team drilled 86 deep holes into the ice, each roughly 2.5 kilometers deep. The drilling process used hot water to melt the ice, creating narrow shafts that reached far below the surface. Each hole required a large amount of energy, on the order of 18,000 liters of fuel per hole to heat the water and keep it flowing. In total, hundreds of thousands of liters of ice were melted to make room for the strings of detectors. After each string of DOMs was lowered into place, the water in the shaft refroze, locking the instruments into the clear ice for good. Life and work at the Amundsen Scott South Pole Station are demanding. The isolation, cold, and altitude create a challenging environment for the scientists, engineers, and technicians who keep IceCube running. Yet, despite these difficulties, a few hundred researchers coordinate to monitor the detector, process the incoming data, and extract meaningful signals from the background. Their efforts make it possible to observe some of the rarest interactions in the universe without leaving our planet. Neutrinos are often described as the phantoms of the particle world. They slip through matter almost unnoticed, leaving very little behind. It takes inventive ideas and large-scale instruments to detect even a small fraction of them. Compared to particles like electrons, protons, and photons, neutrinos remain less well understood. We are still working to pin down their masses precisely, to understand how they transform from one type or flavor into another as they travel, and to see whether they hide any surprises that fall outside the standard model. Even so, neutrinos already play a central role in modern physics and cosmology. They help shape how structures formed in the early universe. They influence the behavior of supernova explosions and the cooling of dense stellar remnants. With every neutrino that is detected and analyzed, we gain a little more insight into these processes and into the laws that govern them. Each event is a small data point, but over time they build up into a clearer picture. In this sense, IceCube and similar observatories are not only watching current events in the cosmos, they are also helping us probe deep questions about the past. One of the biggest questions in science is how everything began. What were the conditions at the very earliest moments of the universe? How did the first particles and atoms form? Why did the universe evolve into the complex structure we see today, with galaxies, stars, planets, and eventually life? From many different lines of evidence, scientists have developed a broad framework known as the Big Bang Theory. This theory does not describe an explosion in space, but rather a rapid expansion of space itself from a much hotter, denser state. Over time, the universe cooled. Protons, neutrons, and electrons formed. Then simple nuclei and atoms appeared. Later still, gas clouds collapsed into stars and galaxies. The details of this story have been tested using observations of distant galaxies, measurements of the cosmic microwave background, and studies of how light interacts with matter in stars and gas clouds. One of the tools used to work out this history is spectroscopy, the study of how matter absorbs and emits light at specific wavelengths. When light passes through a gas or is emitted by a hot object, it carries a pattern of lines that act like a fingerprint for the elements present. By examining the spectra from stars and galaxies, astronomers can tell which elements are there and in what approximate proportions. These observations, combined with nuclear physics, allow us to reconstruct how elements were formed in the early universe and in later generations of stars. The picture that emerges is a bit like assembling a puzzle. Each measurement, a light curve, a spectral line, a background radiation map is a piece that must fit with the others. When many pieces fit together, confidence in the overall picture grows. But sometimes, a piece seems out of place. Its shape does not match the gap where we think it should go. In cosmology, such mismatches can signal that our understanding is incomplete or that there is an effect we have not accounted for. In work related to the early universe, one such troubling piece involves a very familiar element. It is something we encounter in daily life in many forms. It is used in certain medicines and in some metal alloys. It is especially important in the rechargeable batteries that power many of our phones and portable devices. According to our best models of the Big Bang and the nuclear reactions that followed shortly afterward, this element should have been produced in specific amounts. Yet when we look out into the universe and measure how much of it is actually present in old stars, we find less than expected. This element, so common in our technology, is strangely missing from the cosmos, at least in the quantities our theories predict. So we arrive at a simple but serious question. If our theories are right, where is all the lithium the universe was supposed to make? Lithium is not some rare, exotic element that exists only in laboratories. It is familiar and practical. It shows up in medical treatments, in special metal alloys, and most famously in the rechargeable batteries that power many of our phones, laptops, and other portable devices. Yet when we look far out into space and back in time, the amount of lithium we actually see does not match what our models of the early universe tell us to expect. To understand why that is a problem, it helps to review what lithium is at a basic level. Chemically, lithium is one of the alkali metals, the group that also includes sodium and potassium. At room temperature, it is a metal that is surprisingly soft. A piece of pure lithium can be cut with an ordinary steel knife. It does not behave like a hard, shiny block of iron. In school experiments, you might have seen a small piece of lithium dropped into water. It reacts quickly and visibly, producing lithium hydroxide and hydrogen gas. The gas can catch fire, giving a lively demonstration of how reactive the metal is. In modern technology, lithium's most important role is in energy storage. Lithium atoms can easily give up their outer electron, and they can also accept it back under the right conditions. This makes lithium very useful in rechargeable batteries, where electrochemical potential is what matters. Lightweight lithium-based cells can store a lot of energy relative to their mass, which is why they are used in many electronic devices. For cosmology, though, the most important feature of lithium is not its reactivity or its use in batteries. It is its internal structure. A lithium nucleus contains 3 protons. That makes it the third element in the periodic table, after hydrogen with 1 proton and helium with 2. Lithium nuclei also contain a small number of neutrons, depending on the isotope. But the key point is that lithium is very light. Only a few elements are light enough to be made in large quantities in the very early universe, when conditions were hot and dense but simple. Lithium sits at the edge of that group. This is where the puzzle appears. The Big Bang model, combined with our understanding of nuclear physics, tells us that the early universe should have produced a specific mix of light elements, mostly hydrogen and helium, with smaller amounts of deuterium, heavy form of hydrogen, helium-3, and lithium. When we look at very old stars and gas clouds, which are thought to preserve the early chemical makeup of the universe, we find that hydrogen and helium appear in roughly the expected amounts. Deuterium also matches predictions fairly well. Lithium, however, does not. The measured abundance is much lower than the model says it should be. This mismatch is known as the lithium problem, or lithium discrepancy. To see why this matters, we need to look at how the Big Bang picture arose in the first place. In the 1920s, astronomers began to notice that distant galaxies are, on average, moving away from us. Their light is shifted toward longer wavelengths, a sign that space between us and them is stretching. A Belgian priest and cosmologist named Georges Lemaitre suggested that if the universe is expanding now, then in the past, it must have been smaller and denser. If you play the expansion backward in time, you reach a state where matter and energy are crowded into a much smaller volume. From this reasoning came the idea that the universe began in a very hot, very dense state and has been cooling and expanding ever since. If you continue to rewind far enough, you run into a point where the densities and temperatures become so extreme that our usual equations break down. In simple language, all the energy of the universe would be squeezed into an extremely small region. In the mathematics of general relativity, this leads to what is called a singularity, where quantities like density and curvature become infinite. Because this picture involves extremely high temperatures, it is often called the hot Big Bang model. The term Big Bang itself can be misleading because it sounds like an explosion happening in already existing space. The modern view is that space itself was expanding from an earlier, hotter state. The details of that earliest instant, however, are not well described by our current theories. Einstein's equations of general relativity are powerful tools for describing gravity and the motion of matter in curved spacetime, but they are not designed to handle true infinities. When we push them back to the singularity, they stop giving sensible answers. This is why cosmologists say that the very first moment of the universe is hidden from us, at least with the physics we know now. We do not yet have a complete theory that combines general relativity and quantum mechanics in a way that can describe those conditions. We also have no direct evidence from before. That moment, if such a before even makes sense. Any signals that might have existed prior to the hot phase would have been wiped out by the extreme environment, like a fragile pattern thrown into a furnace. Something happened to start the expansion, but our present equations cannot say exactly what or why. What we can say with more confidence begins just after that unknowable instant. The temperature and density were still enormous, but finite. In the earliest fractions of a second, the universe was filled with a hot soup of fundamental particles and radiation. There were no atoms yet, only quarks, gluons, leptons, and photons in a high-energy mix. As the universe expanded, it cooled. The average energy of the particles declined, and new processes became possible. Even a very short time after the start, the conditions changed enough for us to use known physics with some reliability. Around 1 second after the beginning of the expansion, the temperature of the universe is thought to have dropped to about 10 billion degrees Celsius. That is still incredibly hot, but it is a helpful reference point. For comparison, the core of our sun has a temperature of roughly 15 million degrees Celsius. So at this early time, the universe was only about 1,000 times hotter than the sun's center, rather than unimaginably hotter by many orders of magnitude. At 10 billion degrees Celsius, particles were still moving at enormous speeds, and the energy of their collisions was extremely high. Under such conditions, atomic nuclei could not yet form and remain stable. Any attempt by protons and neutrons to bind together into a nucleus would be quickly undone by intense radiation and violent impacts from surrounding particles. Matter, in the sense of long-lived atoms or even simple nuclei, could not yet exist. The universe at 1 second old was still a dense plasma of free particles and light, cooling but not yet ready to assemble the building blocks that would later lead to elements like lithium. In the very early universe, the temperatures were so extreme that even the strong nuclear force, the force that normally binds protons and neutrons together inside atomic nuclei, could not keep anything stable. Any attempt at forming a nucleus would be torn apart almost immediately by the intense radiation filling space. In practical terms, this means that, at first, almost everything existed in the form of high-energy particles and radiation, rather than as matter in any familiar sense. A faint remnant of that early radiation still surrounds us today. As the universe expanded and cooled, the original glow stretched into longer wavelengths and lower energies. We now observe it as a nearly uniform bath of microwave radiation coming from all directions in the sky, called the cosmic background radiation. Its existence and detailed properties are one of the key pieces of evidence that the hot Big Bang picture is broadly correct. This glow is like a snapshot of the young universe, long after the first instant, but still very early in its history. The universe did not stay in that purely radiative state for long. As space continued to expand, temperatures fell. Only about 99 seconds after the expansion began, the temperature is thought to have dropped to around 1 billion degrees Celsius. That is still unimaginably hot by everyday standards, but it is low enough that the strong nuclear force can finally start to do its job effectively. At this stage, the first stable protons had already appeared, and some neutrons were also present. Protons began to bind with neutrons to form the simplest composite nuclei. The most basic of these is ordinary hydrogen, whose nucleus is just a single proton. Alongside it, another important form appears, deuterium. Deuterium is an isotope of hydrogen, meaning it has the same number of protons, one, but a different number of neutrons. A deuterium nucleus contains one proton and one neutron. Because protons and neutrons are now able to stick together without being ripped apart immediately, deuterium nuclei can form and survive for long enough to participate in further reactions. Hydrogen and its isotopes dominate the mix. In the early universe, most nuclei are simple, with very few protons and neutrons. But the environment is still energetic enough that nuclei can collide and fuse, building up slightly heavier elements. When hydrogen nuclei, that is, protons, smash into each other or into deuterium and related combinations, they can undergo nuclear fusion. Through a sequence of reactions, these processes create helium, whose most common isotope has 2 protons and 2 neutrons in its nucleus. Helium is more complex than hydrogen, but it is still a very light element by atomic standards. When cosmologists run the relevant nuclear equations for these early conditions, they find that the outcome is mainly hydrogen and helium, with very specific proportions. The calculations show that, by mass, the matter produced in this Big Bang nucleosynthesis phase should be about 76% hydrogen and about 24% helium, with only tiny amounts of other light elements. These numbers refer to the composition right after this early phase of element formation, long before stars begin to alter the mix. Extremely rarely, under the right conditions, fusion reactions can go one step further. In a small fraction of cases, another proton is added to an existing nucleus, or chains of reactions lead to nuclei with 3 protons. When that happens, isotopes of lithium can form. Lithium has 3 protons in its nucleus, and depending on how many neutrons are present, you can have different isotopes, such as lithium-7 with 4 neutrons, or lithium-6 with 3 neutrons. The calculated amount of lithium produced in this early universe scenario is tiny compared to hydrogen and helium. By mass, lithium from Big Bang nucleosynthesis should make up only a few millionths of a percent of all matter. Written out, the predicted fraction is around 0.0000007%. Even though this fraction is very small, it is still a clear prediction. The standard Big Bang model, plus known nuclear physics, does not say that there will be no lithium. It says there should be a little, and it tells us roughly how much. The mystery starts when we check these predictions against observations. Astronomers use light to measure element abundances in stars and gas clouds. When light from a star passes through its own atmosphere or through a cloud of gas, the atoms of different elements absorb and emit light at specific wavelengths. By splitting starlight into a spectrum and looking at the pattern of dark and bright lines, scientists can identify which elements are present and estimate their relative amounts. By studying very old stars, especially those in the outer parts of our galaxy or in small ancient star systems, astronomers hope to see conditions close to those in the early universe before many cycles of star birth and death changed the chemical mix. When they do this, they find something interesting. For hydrogen and helium, the measurements broadly agree with the predicted proportions. Our own sun, for instance, is roughly 71% hydrogen by mass, 27% helium, and about 2% heavier elements combined. The difference between these numbers and the pure Big Bang values can be explained. The sun has had billions of years to undergo nuclear fusion in its core, gradually converting some hydrogen into helium and heavier elements. Other stars show similar patterns. On larger scales, averaging over galaxies and interstellar gas, the overall ratios of hydrogen and helium in the universe match the expectations from Big Bang nucleosynthesis quite well. This agreement is considered one of the strongest supports for the hot Big Bang model. Lithium, however, does not cooperate. Even though the predicted mass fraction is very small, the actual amount of lithium observed in old stars is smaller still. In fact, the observed abundance of lithium seems to be lower than the predicted value by a factor of about 3. Put another way, for every 3 lithium atoms, that the model says should exist in these early environments, we see only one. This mismatch is not limited to a single star or region. As astronomers examine more and more old, metal-poor stars, stars that have very few elements heavier than helium, the same shortfall appears. The way we look back in time in astronomy is by looking farther out in space. Light from distant stars and galaxies takes time to reach us, so the more distant an object, the earlier in its history we see it. By examining the spectra of stars that are very far away, we sample earlier and earlier stages of the universe's chemical evolution. In principle, this gives us a way to test the Big Bang nucleosynthesis predictions directly. Yet, wherever we look at these ancient, primordial-like stars, we do not find as much lithium as the standard calculations suggest we should. There is another layer to the lithium puzzle involving its isotopes. The main isotope produced in the early universe is lithium-7, with 3 protons and 4 neutrons in its nucleus. This is expected to be the dominant form. A second isotope, lithium-6, has 3 protons and 3 neutrons. Lithium-6 is less tightly bound and more fragile in nuclear reactions. Standard calculations predict that it should be much rarer than lithium-7, making up only a tiny fraction of all lithium nuclei. The expected ratio is on the order of 2 lithium-6 nuclei for every 100,000 lithium-7 nuclei. When astronomers look at certain environments and attempt to measure the relative amounts of lithium-6 and lithium-7, they sometimes find that lithium-6 appears to be more common than the standard models predict. In some cases, analyses suggest that lithium-6 is present at levels up to 1,000 times higher than expected. This suggests not only that the total amount of lithium is off, but that the balance between its isotopes is also unusual. These findings together make the lithium problem more than a minor detail. On one side, the total lithium abundance in old stars seems too low compared to the predictions of the hot Big Bang model. On the other side, the relative amount of lithium-6 compared to lithium-7 appears too high. Both trends point to gaps in our understanding either of the early universe, of how stars process and deplete lithium over time, or of how we interpret the observational data. Does this mean that the Big Bang model itself is fundamentally wrong and that we have to abandon it entirely? Most cosmologists would say no, or at least not yet. The model is supported by multiple independent lines of evidence: the cosmic background radiation, the large-scale distribution of galaxies, the general abundances of hydrogen and helium, and more. The lithium discrepancy is serious, but it affects one part of the story rather than the whole structure. Still, it could be a sign that some piece of physics is missing from our current picture. Broadly speaking, there are 2 kinds of explanations scientists consider when faced with a tension like this. One is that our basic model of the early universe, including the hot Big Bang and the way light elements formed, is incomplete and needs to be revised or extended. This might involve new particles, new interactions, or changes in the conditions during Big Bang nucleosynthesis. The other is that our understanding of how lithium behaves after that early phase, especially inside stars and in galactic environments, is not yet accurate enough, and that processes we have not fully accounted for are destroying or hiding lithium in ways that skew our observations. When faced with something like this, one of 2 things must be true. When scientists face a problem like the lithium discrepancy, the possibilities narrow to 2 broad paths. Either the way we are looking at the universe is flawed, or the framework we are using to interpret what we see is incomplete. In short, either our observations are off, or our models are missing something. To make progress, both options have to be examined carefully. It is difficult to simply discard the hot Big Bang picture No other model does as good a job of explaining several key observations at once: the existence and detailed structure of the cosmic background radiation, the nearly uniform glow left over from the early universe, matched the predictions of a hot, dense beginning that later cooled. The relative amounts of hydrogen and helium that we see in very old stars and in intergalactic gas also line up very closely with what Big Bang nucleosynthesis calculations give. The agreement is not rough or accidental. The numbers come out in ways that would be hard to call a coincidence. That said, the Big Bang model, in its simplest form, is not treated as untouchable. Cosmology is an active field, and even central ideas are open to refinement. For many years, the standard view was that if you followed the expansion of the universe backward, you arrived at a true singularity, a point where density and temperature became infinite and the laws of physics as we know them simply stopped working. Some leading physicists strongly supported this picture early in their careers. Later, some of those same researchers became more cautious about taking the singularity literally. Stephen Hawking is a famous example. He worked with Roger Penrose on mathematical results that showed, under certain assumptions, that singularities were unavoidable in general relativity. Those results became widely accepted, and the idea of a Big Bang singularity became part of the standard story. But decades later, Hawking wrote that he had changed his mind. Once quantum effects are taken seriously, he suggested, the classical singularity may disappear, replaced by a more subtle quantum state that does not involve infinite values. The details of those quantum ideas are complex and go beyond what we need here. But the main point is that even the origin concept at the heart of the Big Bang picture is still being refined. These possible quantum modifications to the earliest moments do not automatically solve the lithium problem. They might change what happens extremely close to the beginning, while most of the light element production we are talking about takes place a bit later, when the universe is already a few seconds to a few minutes old. Still, this discussion highlights that our understanding of the universe's first moments is a work in progress. It is entirely possible that future theories, which combine general relativity and quantum mechanics more fully, could adjust the conditions during nucleosynthesis enough that lithium production naturally shifts to the observed values, while the overall structure of the Big Bang picture remains intact. In that case, the puzzle piece of lithium abundance would eventually click into place alongside hydrogen and helium, without forcing us to abandon the broader framework. The other main option is that the issue lies in our measurements rather than in the basic model. There are some reasonable grounds for considering this. Lithium is present in very small amounts compared to hydrogen and helium, and that makes it intrinsically harder to detect. When we look far back in time, we are looking at very distant objects, and the light we receive is faint and stretched. Extracting precise information about trace elements from such light is technically demanding. The main method for probing the composition of gas between stars, the interstellar medium, is to analyze how it absorbs light from background sources. A bright object, such as a star or a quasar, shines through a nebula or a gas cloud. Different elements in that gas absorb light at specific wavelengths, leaving a pattern of dips in the spectrum. By studying these absorption lines, scientists can infer which elements are present and estimate their relative abundances. This works well for certain elements under good conditions, but as distances increase and signals weaken, it becomes more and more difficult to make accurate measurements, especially for rare components like lithium. At very large distances, the interstellar medium becomes hard to measure directly, The lithium signal can be buried in noise or blended with other lines. In those cases, researchers often turn to primordial stars as proxies for the early universe. These are stars that formed a very long time ago and have extremely low levels of heavy elements. Because they have not been enriched by many generations of stellar birth and death, their chemical makeup is thought to be close to the composition of the gas from which they formed, which in turn should reflect early cosmic abundances. However, stars are not passive containers of the elements they start with. They are active physical systems where nuclear reactions, convection, and mixing constantly reshape their interiors. The outer layers, which produce the light we see and from which we measure element abundances, are influenced by processes occurring deep inside. In particular, lithium is relatively easy to destroy in stellar interiors. At temperatures reached in many layers of a star, lithium nuclei can undergo reactions that break them apart, turning them into other elements. If mixing brings lithium-rich material from the surface down into hotter regions and then back up again, the total surface lithium can gradually be reduced over the star's lifetime. This means that a star's current surface lithium abundance may be lower than the amount of lithium that was present in the gas cloud when the star first formed. Different stars may also deplete lithium at different rates, depending on their mass, rotation, internal structure, and age. If these depletion processes are stronger or more complex than our models currently assume, then the low lithium levels we observe in primordial stars might not directly reflect the original Big Bang output. Instead, they might be the result of billions of years of internal processing. The picture is further complicated by the isotopes. Lithium-6 is more fragile than lithium-7. It can be destroyed at lower temperatures and through different reactions. Yet, some measurements have indicated that lithium-6 might be more common in certain stars than simple models predict. One possible explanation is that lithium-6 is being produced later by processes other than Big Bang nucleosynthesis, such as interactions between cosmic rays and interstellar gas. Another is that some of the spectral signatures we attribute to lithium-6 might be affected by subtle line shapes, turbulence, or blending with other atomic features, leading to overestimates. All of this suggests that our observational situation is not as straightforward as counting atoms in a bottle. The data we have come from complex environments and require careful interpretation. If future telescopes, better models of stellar interiors, and more accurate spectral analyses improve our view of lithium in both stars and interstellar gas, the apparent discrepancy could shrink. It is possible that more precise measurements of truly primordial gas, such as that found in very distant, nearly pristine clouds, will show lithium levels closer to the theoretical predictions than current stellar data do. In that scenario, the lithium problem might turn out to be less severe than it appears today, or even largely resolved by improved understanding of how lithium is processed and hidden in stars. It is also possible that a combination of small adjustments, modest changes in nucleosynthesis conditions, plus refined models of stellar depletion will bring theory and observation into alignment. From that perspective, the problem may be a signpost pointing toward more detailed, but not necessarily radical, corrections. Regardless of which path is closer to the truth, the guiding principle remains the same. A theory of the universe's origin and early evolution is only as strong as its ability to match all available data. Hydrogen and helium abundances agree impressively well with the hot Big Bang framework. Lithium does not yet fit as neatly. Other elements pose their own puzzles. For example, the amount and distribution of very heavy elements such as gold raise questions about how often certain rare events like neutron star mergers or special kinds of supernovae, actually occur. Each of these discrepancies is a small tension between what the model predicts and what the universe displays. In a sense, these tensions are not signs of failure, but opportunities. They highlight where our knowledge is incomplete and where new physics, better observations, or more refined models may emerge. It is remarkable that we are able to reconstruct any part of the universe's early history at all, given how far removed we are in both time and space from those events. Using only light, neutrinos, gravitational waves, and the tools of mathematics, we can infer the conditions that existed when matter was just beginning to form from a sea of radiation. The overall picture we have built is like a large, detailed jigsaw puzzle laid out on a table. Many pieces fit tightly together. The expansion of the universe, the cosmic background radiation, the large-scale structure of galaxies, and the broad pattern of light element abundances. A few pieces, like lithium and certain heavy elements, still resist being placed. They do not invalidate the picture, but they tell us that some regions of the puzzle need more attention. Underlying this effort is the assumption that the universe follows consistent rules. There is an order to how matter and energy behave, even under extreme conditions. That order allows us to write equations, build models, and test them against observations. When a mismatch appears, like the lithium discrepancy, it is a signal that we have not yet captured all of the relevant rules, or that we are applying them in an incomplete way. The search for a resolution is not just about one element. It is about refining our understanding of the fundamental laws that govern everything. It is reasonable to expect that, over time, the lithium problem will find its place in this evolving picture. Perhaps new observations will show that our current measurements were biased. Perhaps new theoretical ideas will adjust the early universe conditions in subtle but important ways. Perhaps improved models of stellar behavior will reveal that stars have been hiding or destroying lithium more efficiently than we realized. Whatever the path, the question exerts a strong pull. It ties into our broader desire to know not only what the universe is like now, but how it came to be. Some questions in science carry special weight. Questions about origins of the universe, of structure, of matter itself, fall into that category. They are not only technical problems, they connect with our sense of place in the cosmos. Because of that, they are hard to set aside. The lithium puzzle is one piece of this larger story. It may be small compared to the full sweep of cosmic history, but it acts as a sensitive test of our ideas about the beginning. The work of aligning every element, every ratio, and every observation with our models is ongoing. As measurements become more precise and theories more complete, the gaps between them should narrow. One day, the discrepancy in lithium may be as well understood as the abundances of hydrogen and helium are today. When that happens, the overall picture of the universe's early moments will be that much clearer, and another piece of the cosmic puzzle will have found its rightful place.